Of any episode that I do in this entire series, this is my favorite because this, my friends, is cryptography. Cryptography is the science, the study of taking data and making it hidden in some way so that other people can't see it, and then bringing the data back. So the big word we want to use when we talk about cryptography is taking some kind of information and providing confidentiality to that. Now, we do this through a number of different ways, but the magic word I want to use right now is obfuscation. Obfuscation is to take something that looks like it makes sense and to hide it so that it does not make sense to the casual outside observer. Now, there's a lot of different ways we can do obfuscation to provide confidentiality. One of the things we can do is diffusion. So here's a picture of my grandson right here. Let's take a look at that. That's Stephen. Isn't he gorgeous? So what I'm going to do is I'm going to diffuse this image and make it fuzzier. Now, in this particular case, we didn't diffuse it too much, so if you look at it, you could probably tell there's still a cute little kid there, and he is cute. But diffusion only allows us to make it less visible, less obvious. Now, what we can also do is confusion. So let's take that same image of Stephen one more time and just stir it up. Let's just make a mess out of it. Now, in this particular case, we've created a lot of confusion of the image. It's basically stirred up, and it would be very difficult for somebody to simply look at this and go, ah, that must be Mike's grandson, Stephen. So the other challenge we have with cryptography is we go through this process of taking some kind of data, and we go through this obfuscation process. But, and here's the important one, is that we've then got to take this obfuscated data and some way bring it back into its original form. So we call this encryption and decryption. And cryptography is the process of making this happen. Cryptography's been around for a long, long time. In fact, probably one of the oldest type of cryptography's ever been around is something called the Caesar cipher. I don't know about you, but when I was a little kid and I was eating a box of cereal, you'd dump out the box of cereal and you'd get some kind of prize inside. And one of the things we'd get is called a secret decoder ring. So what I want to do here, can we put up a picture of a secret decoder ring real quick? Okay, so this is a classic old school kids decoder ring. Now, what I want to do is I've made my own decoder ring right here. And I'd like us to take a little peek at this guy. And what you're going to see here is I've basically got a wheel with all the letters of the alphabet, A through Z. And on the inside, I've got letters of the alphabet, A through Z. So right now I've got them lined up, A to A, B to B, C to C. Now, what I can do to make a secret code is, let's say I can I can rotate this 2 times. And what we can do is we can take our original plain information, what we call the plain text, our message that we want to encrypt, and we just change the letters. So we call this substitution. What we'll do is we'll take one value and substitute it for another. Now in this case I've rotated it twice, so we actually have a term for this. We call it ROT2, just like that. And if I turned it 3 times, it would be ROT3. Now, so we can take like the word ACE, A-C-E, and I can change ACE to C-E-G. Get the idea? So that's the cornerstone of the Caesar cipher. So to convert something with a Caesar cipher, and as a matter of fact, let's just go through the process real quick. Now, what I'm going to do, let's put up a piece of plain text that we want to encrypt. We attack at dawn. So here it is, we attack at dawn. Now, the first thing we're going to do, get rid of all the spaces. So now it just says, we attack at dawn, very readable. We don't worry about upper or lower case in this particular situation. Now, let's go ahead and put our groovy little secret decoder ring up there, and let's go ahead and turn it, in this particular case, 5 times. All right? So we're doing an ROT5. So let's turn it 1, 2, 3, 4, 5 times. So now what we can do is, by using the secret decoder ring, we can go ahead and encrypt we attack at dawn as follows. So what we now have generated is a classic Caesar cipher. Now there's a problem with Caesar ciphers, and the biggest problem we have with them more than anything else is that, in fact, people who buy crossword puzzle books will pay money to be able to do this, is that we can decrypt them we can, just by looking at them, we can provide what's known as cryptanalysis. Cryptanalysis is breaking these encrypted codes. So the problem is that anybody who's good at these things could pretty easily crack this. So the Caesar cipher, even though it is a substitution cipher, does have the problem is that it's just too easy to predict what this is because we're used to looking at words. So what I want to do is make it a little bit more challenging. The first thing I'd like to try to do is I want to bring in something called the Vigennet cipher. The cornerstone of Vigennet cipher is that it's really just a Caesar cipher with a little bit of extra confusion involved. So what I've got here is a table that shows all the possible Caesar ciphers there are. So here up at the top we're going to have the word plain text. I'll show you how that works in just a minute. And then you'll see on the far left-hand side it says 0 through 25. So these are all the possible ROT values you can have, from ROT 0, which means A equals A, B equals B, all the way down to ROT 25. So what we're going to do, let's hold on to this for a minute, and now let's go ahead and start with a piece of plain text. Let's use "we attack at dawn" one more time. And what I'm going to do this time is we're going to apply a key. The key is simply a word that's going to help us do this encryption. In this particular case, I'm going to use the word FACE, F-A-C-E. Now, what I'm going to do is I'm going to put F-A-C-E above the first 4 letters of "we attack at dawn." So here we go, F-A-C-E. And then I'm going to just keep repeating that. So let me put FACE again. I'm going to put FACE again. And you'll see I've got 2 letters left over. No big deal. I'll just put F-A. And what we've done is we have applied a key to our plain text. Now, what we're going to do is we're going to use the key to change the Caesar cipher ROT value for every single letter. So let's go ahead and do this. Now, what I'm going to do is I'm going to reference my little chart here. So the first letter of the plain text is the W in "we." So here's the W up at the top. And the key value is F. So let's go down on the y-axis here until we get to an F. Now you see that F, you'll see the number 5 right next to it. So this is ROT 5. So all I need to do is do the intersection of these, and we get the letter B. Great, let's do it again. Now in this case, the second time, it's the letter E from "we," and in this particular case, the key value is A, which is kind of interesting because that's ROT 0, but that still works. So we start up at the top, find the letter E, then we find the A, and in this case, because it's ROT 0, by coincidence, E is going to stay as E. Let's do the third value. Now this time it's the A as an attack. So we go up to the top, there's the letter A, and the key value is C as in Charlie. So we go down to the C, that's ROT 2, and we then see that the letter A is now going to be C. Okay, let's do one more real quick. In this particular case, it's the first T in attack. So we come over to the T's, and now the key value is E as in face. So we go down here, that's ROT 4. We do the intersection, and now we've got an X. So the first 4 letters of our encrypted code is BECX. So let's go ahead and run through and do the rest of these real quick. I'll just put those in for you. And we have now encrypted in the Vigennet style. So the beauty of the Vigennet is that it actually gives us all the pieces we need to create a classic piece of cryptography. Number 1, we have an algorithm. And the algorithm are the different types of Caesar ciphers and the rotations. And second, we have a key. And the key allows us to make any type of changes we want within ROT 0 to ROT 25 to be able to encrypt our values. Any algorithm out there is going to use a key in today's world. So when we're talking about cryptography today, we're always going to be talking about algorithms and keys. Now the problem with the Vigennet is that, well, number 1, it's surprisingly crackable. Isn't that interesting? But the bigger problem is Vigennet works just great for letters of the alphabet. Unfortunately, it's terrible for encrypting pictures or SQL databases or your credit card information. In the computer world, everything is binary. Everything is ones and zeros. So what we need to do is come up with algorithms that provide the type of encryptions and decryptions we need to encrypt and decrypt long strings of just ones and zeros. Now, if you look at a string of ones and zeros, you go, how does anybody make anything out of this? Well, they do. You got a string of ones and zeros, may look like nothing to you, to a human being, but to Microsoft Word, that could be a Word document, or it could be a voice over IP conversation, or it could be a database stored on a hard drive. I don't know, but just because as human beings we look at long strings of ones and zeros and get confused, trust me, the computers don't. What we need to do, though, is we need to come up with algorithms which, unlike Caesars or Vigenet's, that will work with binary data. Now, luckily for us, there are a lot of different ways to do this. So what we're going to do is I've got an example of an algorithm we're going to use that encrypts a simple phrase that we're going to convert those to binary, by the way, and we're going to do this using a very interesting type of binary calculation called exclusive OR. For our first encryption, I'm going to encrypt my name. So here's my name, Mike, M-I-K-E. Now, the first thing we're going to have to do is we're going to have to convert this to the binary that a computer would use. So I'm going to be using the binary equivalents of these text values. So let me go ahead and convert these into their binary equivalents. And anybody who's ever looked at ASCII code or Unicode should be aware that we can convert these into binary. Okay, so here we go. So here's M-I-K-E converted into binary. Now notice that each character takes 8 binary digits. So we've got 32 bits of data that we need to encrypt. So that's our clear text. Now, in order to do this, we're going to need 2 things. First of all, we're going to need an algorithm, and then we're going to need a key. Now keep in mind, what I'm making up is like the most simple version of encryption you can possibly do. So let's go ahead and first of all set up our algorithm. Now our algorithm is extremely simple, using what we call an exclusive OR. So here's the exclusive OR. This is what we call a truth table. So what I'm going to do is I'm going to choose, because this Mike algorithm arbitrarily chooses this, is I'm going to be using a 5-bit key. Now, there's a reason I'm using a tiny, tiny short key like this. In the real world, keys can be thousands of bytes long. But for right now, we're just going to use a 5-bit key. So to make this work, let's start placing the key. So I'm going to put the key over the first 5 bits. So here at the letter M for Mike. And now we can look at this table and we can start doing the conversion. So let's convert those first 2 values, then the next, then the next, then the next. Okay, so now we've converted a whole key's worth, but in order to keep going, all we have to do is schlep that key right back up there, okay? In fact, let's go ahead and extend the key all the way out. Boop, 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 boop. So now the key, we just keep repeating it. And you'll see here at the end, it doesn't quite line up. No problem. Just add whatever amount of key you need to go ahead and fill up the rest of this. So there we go. Okay. So now we can go ahead and complete this. Now, let's just do it fast. You can double check me if you want. But as we go through here, using the exclusive OR algorithm, we then create our ciphertext. Go ahead and spot check a couple of those for me and make sure I got them right. Okay, beautiful. Now, so this is the ciphertext. Notice that we have an algorithm, which is extremely simplistic. We have a key, which is very, very simple and short. But we now have an absolutely perfect example of binary encryption. Now to decrypt this, we'd simply reverse the process. So I'm not going to go through all that, but appreciate that we would take the ciphertext, place the key up to it, and then basically run the algorithm backwards, and then we would have the decrypted data. So even though we've only seen 3 types of encryption so far, keep in mind that these really do everything that we're going to be seeing in later episodes, just a lot more complicated. Now, a couple of things we need to think about here. First of all, what's interesting is that if we always have an algorithm and a key, there is a gentleman named August Kirchhoff who came up with a very, very interesting concept. Kirchhoff's principle says this: as long as you don't know what the key is to an encryption, you can actually understand the algorithm completely. Now this is really, really important. Today's big super duper encryption tools that we use out there to protect you on the internet are all open standards. Everybody knows how the algorithms work. Now you would think, wait a minute, now if I know how the lock works in essence, wouldn't I be able to pick it easier? And the answer is, interestingly enough, no. In our society, by showing everybody the lock, everybody can check the lock to make sure it isn't pickable. So when we talk about proprietary encryptions, everybody gets nervous because if we don't all know how the lock works, we can't all test the lock to make it work. So Kirchhoff's principle, and something we stand to today, simply says, everybody knows the algorithm, but if you don't know the key, it's not going to do you any good.